Good morning everyone, and welcome to today's worked exam answer video. Today I'm having a look at a transition metal and reactions of metal ions in aqueous solution question. They've kind of merged the two things together when it comes to the final part of the question down here, where we've got this little reaction scheme. Initially it starts off with transition metals, thinking about colour, and then we go on to some reactions that are ligand substitution and some reactions that are from the metal ions reacting with the bases, so ammonia in this case. So there are a couple of other bits on the back of this as well, so a bit of a longer question. I will try and be as concise as I possibly can. So starting off, we are told that copper 2 complexes are coloured, and they've given us a little bit of information that we would normally have to give ourselves when we explain why something is coloured. They've said the colour is caused by d electrons of copper moving from their ground state to an excited state. We're therefore not going to get a mark for saying that in question A, but in other questions that are worth 3 marks, the second mark would be for saying that we have a d electron moving from the ground state to the excited state. So always worth making a note of what you've already been told, because we're not going to get marks for that. And it's also good to see how they've worded it here so that you can word it similarly in your own answers. But we have to explain why aqueous solutions of the CuCl42- ions are yellow, which, if we think about copper complexes, it's weird to think of something copper-based being yellow, but we'll come on to think about why it may be yellow a bit later on. But in terms of explaining why the ions are yellow, first thing, they've given us a specific colour, so we're going to have to use specific colours in our answers. If it was just saying explain why complexes are coloured, full stop, then we could be more general and vague and just kind of say, well, we get colour because this and this. But here, if we know that they're yellow, we're going to have to say that yellow is the colour that is reflected or transmitted, and then recognise that the yellow is the complementary colour to the one that is absorbed in the first place. So normally the 3 marking points we would give here would be 1 for saying that a particular frequency or wavelength of light is absorbed, and that it is the absorption of that light that provides the energy to promote an electron from the ground state to the excited state, and then it's the complementary colour that's reflected or transmitted. Here we're going to have to say specifically what colour is absorbed if yellow is the complementary colour. So we do need to know a little bit about the colour wheel, and complementary colour to yellow is going to be some sort of blue, purple kind of colour. So what I'm going to say here is as follows. So first of all, blue light is absorbed, which would be to promote the electron from the ground state to the excited state, but we don't get any marks for that. I'm adding that here for your context. And then I'm going to say that the yellow light, and then I'm just going to make it clear that I know that that is the complementary colour to the light absorbed. Is reflected, and you can say reflected or transmitted, or mention both. I'm going to mention both here, but either or is absolutely fine. but it's really important that we show that we know that it's not the colour of light absorbed that we see. The colour that we see is the colour that is reflected or transmitted, or reflected and transmitted. Okay. Then we're going on to have a think about specifics. So we need to be aware of how we can calculate the energy gap between the ground state and the excited state when it comes to promoting the electron, or we may, as is in this case, be asked to rearrange that to work out the frequency of the light absorbed or the wavelength of the light absorbed. So here we have been given the energy change when a d electron moves from the ground state to the excited state in a copper complex. So the separation in energy between the ground state and the excited state is that many joules. We've been given Planck's constant, and we always will be given Planck's constant in these questions, and we have to calculate the frequency in seconds to the -1 of the light that is absorbed. Now this is an equation that we're going to need to remember. So delta E, the energy gap, is equal to Planck's constant times by the frequency, or it's Planck's constant times by the speed of light divided by the wavelength. If you are not sure of this equation, we can hopefully use the units to help us. So energy change in joules, Planck's constant in joule seconds, frequency in seconds to the -1. So joule seconds times seconds to the -1 will give us joules. So we know that H is going to need to be multiplied by the frequency in order to get the units of the seconds and seconds to the -1 to cancel. So that can be helpful using the units. So if we want frequency, we've just got to do a simple rearrangement. Frequency is equal to delta E divided by Planck's constant, and then I can sub those numbers in to get my answer. So frequency equals 3.98 times 10 to the -19 divided by 6.63 times 10 to the -34, and that gives me, and I'm going to give my answer to 3 significant figures because that matches the numbers in the question, 6.00 times 10 to the 14 seconds to the -1. Okay. Then in part 3, we've got to think about 3 ways in which a transition metal complex can be changed to alter its colour. Now, as I said before, when we think about most copper things, we think about them being blue. So why is it that the CuCl4 2- ions are yellow? What causes such a big change in colour? 2 things. One, we have got different ligands here compared to what we have in the blue complexes, where we've got water or we've got a mix of water and ammonia, but also we have a different coordination number and a different shape when we have the chloride ion ligands attached compared to when we have the water ligands attached, or the mix of water and ammonia. So that gives us 2 things that we can say straight away. We've got change in ligands, and we've got a change in the coordination number, and thus a change in shape. They're not separate points, we'd have to give them within the same point because coordination number dictates shape. But that's 2 things straight away just from thinking about what we know about copper specifically. But the 3 I would always remember, 1 is the oxidation state of the transition metal, and the example for that, which can help to remind us, is iron 2+ versus iron 3+. Iron 2+ complex ions are green, iron 3+ complex ions are brown, even when we've got the same ligands and the same coordination number. So the oxidation state of the transition metal is important, and then second of all, the ligands that we have within the complex, and that not only means sort of water and ammonia versus chloride ions, but it also means monodentate versus bidentate or multidentate ligands as well. And then third up, we've got coordination number. Which is the number of coordinate bonds formed between the ligands and the transition metal, which, as I said, will ultimately dictate the shape, whether we have tetrahedral, octahedral, square planar or linear as the main examples we need to be aware of. We can also change the transition metal because copper things mainly blue, iron 2+ things mainly green, but if we're thinking about within a transition metal complex where we keep the transition metal the same, those are the three marking points that will always be on the mark scheme. Okay. Then we're having a look at a bit of a reaction scheme down here in which P, Q and R are different complex ions of copper. Now, this is where they've mixed up some transition metal knowledge with some reactions of metal ions and aqueous solution knowledge. So we've got the original CuCl4 2- ion reacting with an excess of water to make P, then reacting with Na4EDTA to give R, and reacting with an excess of aqueous ammonia to give Q. So the excess with the ammonia is important from a reactions of metal ions and aqueous solution point of view. The EDTA is important from a transition metal ligand substitution point of view, and excess water again is thinking about kind of both together actually, ligand substitution and reactions of metal ions and aqueous solution. So first of all, we have to name the shape of the CuCl4 2- ion. So what I would always suggest here is we think about coordination number, first of all, which is 4, because I've got 4 chloride ion ligands forming coordinate bonds with the copper. But if we have a coordination of 4, we then have to decide, is this going to be tetrahedral or is it going to be square planar? And the generic rule is, if we've got chloride ion ligands, which will give us a charged complex, that will be tetrahedral. If it's a neutral complex overall and contains platinum, it's going to more likely be square planar. So first of all, we need to think about the coordination number. And then second of all, think about, is the complex overall charged? Do I have chloride ion ligands or do I not? Do I have platinum and an overall neutral complex? And that's kind of your what your thought process needs to be to figure out that this is going to be tetrahedral. The main complex we need to be aware of with a square planar shape is cisplatin and transplatin. The chloride ion ones will always be tetrahedral, and if you're aware of those, then you should be pretty much okay for the differences between coordination numbers 4. Next up, we've got to give an ionic equation for the conversion of CuCl4 2- to form complex ion P. So what might be useful initially is to think about what complex ion P might be. If we're adding an excess of water, then I would suggest we're going to get water ligands becoming a part of the complex, which makes sense from a ligand substitution point of view, and it also makes sense from a reaction of metal ions and aqueous solution point of view, because when we have these complex ions and we have aqueous solutions of them, we generate the hexa AQA ions. So let's start this equation with the CuCl4 2-, and then let's finish it with what we know complex ion P to be. So CuH2O6, overall charge 2+. And how do I know the overall charge is 2+? Well, in the CuCl4 2-, you would be expected to know that each chloride ion ligand has a charge of -1. So that would give us -4 from the chloride ion ligands, and an overall charge of -2 means that the copper has to be +2 for its oxidation state. So in our product, complex ion P, we have now 6 neutral water ligands, so no charge. And if copper is therefore still +2 for its oxidation state, then the overall charge will be +2. How do I know it's going to be 6 waters and not 4? There are only 4 chloride ion ligands around the copper metal ion because the chloride ion ligands are bigger than the water ligands, and we can't fit 6 of these around the copper, so we won't get octahedral shapes with the chloride ion ligands. It'll always be 4 of them in a tetrahedral arrangement. Also, because they're charged, that also doesn't help to try and fit 6 big charged ions around, because we're going to get some repulsion. But water is smaller, so we can fit 6 around and change to an octahedral shape. And being aware that we have these differences is important, and you might get asked to explain why we only have 4 chloride ion ligands versus 6 water, and that is to do with the size and the charge of these ones. So to complete my equation, I'm going to need to add 6 H2Os. And on the product side, I'm going to need the 4 Cl- ions to be removed. So we can do our swap like so. So that is an ionic equation because we've got charges on our ions here and here, and we've got our Cl- ions here. Charges should be the same on both sides, which they are, and of course all the atoms should be balanced, which they are. Okay. 2 more questions on the reverse side. We're going to be asking about Q and R. So we have to state the colour of the solution containing complex ion Q and given an ionic equation for the conversion of CuCl4 2- to Q, and identify complex ion R. So I'll do all the working on here and then we'll flip back over. So when we think about the excess aqueous ammonia, first thing that we're going to get formed when the CuCl4 2- is reacted with this excess aqueous ammonia is these copper hexaqua ions. Then we would have the ammonia initially acting as a base to take protons from the water ligands to give us the precipitate CuH2O4 OH2, which would be neutral, hence it precipitates. But then copper is the special case, the extra case, where we then need to know in an excess we get a further reaction, which is then the ligand substitution, where we end up with our octahedral shape with 2 waters and 4 ammonias. Now we're going to have to show all of that from the initial formation of CuCl4 2-. So it's not going to be one of the equations that we thought about from the reactions of metal ions and aqueous solution topic, but we do need to know that initially we would get that precipitate, and then that precipitate would dissolve to give us a new solution, and we would need to know the colour of that. So again, I'm going to do the same thing I did for part E. I'm going to have what we start with, what the formula of Q is going to be, and then we can see how to put the rest of the equation together. And because this isn't one that we specifically covered, it's really important that we are able to do it this way. So I would recommend for all of the reactions of metal ions and aqueous solution reactions, being able to fathom them out rather than just rote learn them, because that will really help you with a question like this. So we're starting with the CuCl4 2-, and Q will be the CuH2O2 NH3 solution. And same thing applies here, neutral ligand, copper still in its oxidation state of +2, so overall charge is +2. Then we can think about, well, how am I going to go from here to here? I'm going to need waters, obviously, and I'm going to need ammonias, obviously. Now, we don't need to worry about all the varying steps here. We don't need to think about this originally becoming the hexaqua ion, then getting the blue precipitate with the 4 waters and the 2 OH-, and then it becoming this. We just need to show how we're going from here to here. So I need 2 waters, and I need 4 ammonias. And that will give me complex ion Q. And that is the example that we need to be aware of for our partial ligand substitution from our transition metal topic. We won't get 6 ammonias on here, we get a partial ligand substitution instead. And this also then enables us to show cis-trans isomerism in an octahedral shape where we have 2 different monodentate ligands in this ratio. What else do I need on the product side? I need the 4 Cl-, which need to come off of the original complex ion. That should all be balanced, and our charges should be balanced as well, which I believe they are. This solution is the deep blue solution, and it might seem that saying deep blue or dark blue is really picky, but again it comes back to what we talked about in an earlier question with regards to colour and how the ligands attached affects the colour. When we have the precipitate with the 4 waters and the 2 OH minuses, that is a blue precipitate, but when we then change it and we change the ligands, it becomes deep blue, and I think that's a really nice illustration of how changing ligands can have an effect on the colour, albeit quite slight in this case. So that is our deep blue solution, and it's a solution because it's charged. When we have the precipitates, they're all neutral. As soon as the precipitate has been redissolved or reacted further, we get a charge back on our complex, it will be a solution again. Okay, and finally we just need to identify complex ion R. So we're going from P, so we need to be able to work out what P is in order to do this, which we already have. So P is our CuH2O 6,2+ ion, and EDTA, this is our transition metals knowledge coming into play here. So this is a multidentate ligand. And we need to know that EDTA has the capability of forming 6 coordinate bonds. And that therefore tells us that if we're going to be doing a ligand substitution reaction, that we're only going to need 1 EDTA to take the place of all 6 of the waters. Now, we also need to know the charge on EDTA, and they've been quite nice here in giving us this with Na4 EDTA, so that we can learn that EDTA has a charge of 4-, because that's going to then enable us to work out the overall charge on this complex. So we are going to swap all 6 waters for an EDTA. So it's going to be Cu, and then we can just write EDTA. We only need 1 of them. We don't need any brackets or anything like that. And then for the square brackets, we now need to work out the charge. So copper's in the oxidation state 2+, EDTA has a charge of 4-, 2+, 4-, overall charge -2. And one of the things I didn't explicitly say, and my apologies, I kind of made an assumption, so I'm going to come back. How did this help me to work out that EDTA had a charge of 4-? Each sodium ion would be +1 because sodium is in group 1, so 4+, therefore EDTA has to be 4-. These reactions can be hard, particularly when they build in both topics together, but this is where it's really important that we know sort of the formulae of the products of different reactions so that we can then put the equations together, okay? If anything that I've said in any of this question is unclear, or you want me to clarify anything, or you have similar questions you want me to work on, please, as always, just let me know in the comments. Thank you so much for watching, guys. I really hope the revision is going well, and if there's anything I can do, don't hesitate to let me know. Thank you so much. Bye.